In this video, we're going to be solving a problem on electric potential. The problem is on the board and it states an electric dipole of 2-point charges Q1 equals plus 2 microcoulomb and Q2 equals minus 12 microcoulomb. Oh, plus 12 microcoulomb, rather, is the first one. Is placed 10 centimeter apart. Compute the potential at points A, B, and by potential, I mean electric potential, okay? In the figure below, and here is the figure. This might not be too clear for you guys, okay? So I'm going to draw another diagram up here. Now I'll have something like this, okay? I'll have point B, which is 4 centimeter. I'll have 6 centimeter over here, and then we'll have 4 centimeter over here, okay? And this is Q2, and then we'll have point A, okay? And then we'll have point C, okay? I think that's what we have. That's Q2, and here we're having Q1, and here we're having Q1. And the question wants us to find the electric potential at points A, B, and C. Okay, here is point A, here is point B, and here is point C. First things first, we're going to talk about point A. Now, in our previous video, we talked about how to solve problems or deriving the equations rather on electric potential. Okay, we did say that electric potential has a formula which is electric potential energy divided by the charge. Okay, which is also same as KQ divided by R. Okay, that's the formula. So to find the electric potential at point A, we are going to consider the two charges which are in the system, Q1 and Q2. So for the first one, the electric potential at this point due to Q1 will make use of this formula. For the second one, the electric potential at this point due to this formula, due to this charge Q2 will make use of this formula as well, and then we'll sum both. Okay, so it is that easy. So the electric potential will be equal to KQ1 over R1, which is for the first one, plus KQ2 over R2. Now K is a constant, so we can bring out K, and we're left with Q1 over R1 plus Q2 divided by R2. Okay, now K has a value of 9 times 10 to the power of 9. In brackets, what is Q1? Q1 is having a value of 12 microcoulombs, okay? So we're going to have 12 times 10 to the power of minus 6. What is the distance from Q1 to the point we're looking for? From here to here, that's 4 centimeters, right? This is point A. So that's what now? 6 centimeters rather. From Q1 to point A, we have what now? 6 centimeters. So I divided by 6 plus Q2 is what now? Having a value of minus 12 microcoulombs. So I have minus 12 times 10 to the power of minus 6. Okay, divided by the distance from Q2 to point A was given as what now? Was that 4 centimeters or 4 meters? I think this should be in centimeters. This should be in centimeters. So we might have to convert as well. Please do not make that same mistake. Now 6 centimeters a meter, that's 0.06 meter. Okay? So we're going to have 0.06 meter. And then for the other one, we're going to have 0.04 centimeters. 0.04 centimeter. Okay? So this one is in centimeters as well. Centimeters. Now to complete the final value, we're going to make use of our calculator, which is 9 times 10 to the power of 9. Okay? So we're going to get a value of V, which is the electric potential, as minus 9 times 1, 2, 3, 4, 5 times 10 to the power of 5. Okay? I think those are the correct number of zeros. Okay? Now what's going to be the unit for V? We can quickly get the units, okay? By simplifying what we're having here. U is in joules and Q is in coulombs. So we can write as joules per coulomb, or we could as well say U is in Newton meter, okay, divided by coulomb. So we have Newton meters per coulomb, okay, which is usually the one you find. So we have Newton meters per coulomb, okay. Now that is how we solve a problem like that for V. Okay, that is for point A, electric potential at point A. Now, how about the potential at point B? How are we going to solve a problem like that? Let's solve for the electric potential at point B. So at point B, the electric potential at point B can be solved in this manner. Now for point B, we're going to sum the electric potential of Q1 to this point, and the electric potential of Q2 to this point. Okay, so we're going to do that using the same formula. We're going to have V is equal to K in bracket Q1 over R1 plus Q2 over R2. Okay, so V is having a value of 9 times 10 to the power of 9. Okay, in bracket, what's Q1? Q1 is still having a value of 12 times 10 to the power of minus 6. 12 times 10 to the power of minus 6. Whereby the distance of Q1 to B is what now? 0.04 meter, 0.04 meter. Okay, plus for Q2, this Q2 is having a value of minus 12 times 10 to the power of minus 6 divided by what is the distance from Q2 down to 4, down to point B. So you have 4 plus 6, that's 10, plus 4, that's 14. Okay, so 14 centimeter in meter, that's 0.14 meter. Okay, now if we do the same thing on our calculator, 9 times 10 to the power of 9, okay, times 10 to the power of minus 6 times 12 divided by 0.04 minus 12 divided by 0.14. What are we going to get? We're going to get a value of V as 1, 2, 3, 4, 5, 6. We're going to get 1.93 approximately, okay, times 10 to the power of 6 Newton meters per coulomb. Okay, that's going to be value for the electric potential at point B. Now, how about the electric potential at point C? Point C is just upward, okay, and you can see the total that it is what now is symmetrical. That is distance from here to here is same as distance from here to here. That means the diagram is symmetrical, or it is what now an isosceles what now triangle. Okay, so at point C, what are we going to get? So at point C, we're going to consider the distance from here to here as well as the distance from here to here. Now, they did not give us the distance from these two guys, okay? But how are we still going to solve a problem like that? Let's see what we're going to get. So let's say the distance from here to here is R and from here to here is R. They are both equal. Using the same formula on the board, okay? V equals K in bracket Q1 divided by R1 plus Q2 divided by what now? R2. Okay? So we're going to get V equals K is having a value of 9 times 10 to the power of 9. In bracket, Q1 is having 12 times 10 to the power of minus 6. The distance is what now? R, okay, which is from here to here. And then plus Q2 is minus 12 times 10 to the power of minus 6. Divided by the distance is also what now? R, that is from here to here, okay? Now you notice we're having the same thing, okay? Plus times minus gives you minus. Okay, so from here we're going to have a staggering value of what now? Minus, right? So you're having 12 times 10 to the power of minus 6 over r minus 12 times 10 to the power of minus 6 over r. When you subtract both, you get 0, right? 0 times 9 times 10 to the power of minus 9. What do you get? You get what now? 0, right? So our final value is what now? 0. Now, unlike electric fields rather, when you have to determine a value of 0, most times you don't need to solve, you just have to look at the way the charges are placed at different distance away from the point you have to find the electric field, and so on and so forth. This one is quite different. You still have to solve, okay? You cannot just determine the value to be 0 without solving, okay? So that is how a problem like this is being solved. If you have a question, do put it in the comment section. And more videos will be uploaded in our next video. We're still going to solve a problem on electric potential, okay? A different problem. So do it to click on the notification bell so that when that video is being uploaded, you'll get notified. See you in the next video. Bye.